Hello students, my name is Shubhangi Ajmire. I am from Deccan Education Society's Brihan Maharashtra Vanijya Mahavidyalaya, Pune. Students, today we will learn 6th chapter Linear Programming. Last year, you have studied linear inequation, graphical solution of linear inequation in two variable and solution of system of linear inequation in two variable. Today, we will use this graphical solution to find the maximum and minimum value of linear expression. So let's start with the PowerPoint presentation. For this chapter, there are 6 marks. In this chapter, we will learn meaning of LPP. LPP means linear programming problem, mathematical formulation of LPP, solution of LPP by graphical method. Linear programming problem, in short, it is called LPP. Introduction. Linear programming problem is used in different fields such as management, planning, production, transportation, etc. Linear programming is a mathematical technique designed to help the managers in their planning and decision making. Linear programming problems are also known as optimization problem. Optimization problem means maximization or minimization problem. It is usually used to optimize a certain function called objective function subject to the given condition or restriction known as constraint. Meaning of LPP. A LPP may be defined as the problem of maximizing or optimizing a linear function subject to linear constraint. The constraint may be equation or inequations. Here, the word linear means that all the mathematical functions containing variables of index 1. Now we'll see the terms related to LPP. First term, decision variables. The variables involved in LPP are called decision variable. Objective functions, a linear function of decision variable which is to be optimized, that is either maximize or minimize, is called objective function and it is denoted by Z. Generally, students, we know that manufacturer or businessman always want to maximize the profit and minimize the cost of production. So profit and cost, these two are the objective functions. Third term, constraint. Conditions under which the objective function is to be optimized are called constraints. These are in the form of equations or inequations. Non-negativity constraint. The values of the variable under considerations may be positive or 0, but not negative. Such constraints are referred as non-negativity constraints. Mathematical formulation of LPP. We can formulate real-life problem mathematically as LPP. Steps to formulate the LPP are as follows. First step is identify the decision variable and denote them as X, Y or X1, X2. Second step, identify the objective function, means identify the function which is we have to optimize and write it as mathematical expression in terms of the decision variables. Third step, identify the different constraints and express them as mathematical equations or inequations. Fourth step, write the LPP in mathematical form. The general mathematical form of LPP. The LPP can be put in the following form. Maximize or minimize Z is equals to C1x1 plus C2x2 subject to the constraint A11x1 plus A12x2 less than or equals to B1, A21x1 or A22x2 less than or equals to B2. Equation 2, x1 is greater than or equals to 0, x2 is greater than or equals to 0. Equation 3. Here, the linear function means equation 1 is called the objective function. Second, the linear functions in second equation are called constraint, means A11x1 plus A12x2 is less than or equals to B1, A21x1 plus A22x2 less than or equals to B2 are called constraints. And condition in 3 means x1 is greater than or equals to 0, x2 is greater than or equals to 0 are called non-negativity constraint. Note that student, in this chapter we shall study LPP with only two variables. Problem first. A manufacturing firm produces two types of gadget A and B which are first processed in the foundry and then sent to machine shop for finishing. The number of man hours of labor required in each shop for production of A and B, and the number of man hours available for the firm are as follows. Here, 1 unit of gadget A required 10 hours in foundry and 5 hours in machine shops. 1 unit of gadget B required 6 hours in foundry and 4 hours in machine shop. Total time available for foundry is 60 hours and for machine shop is 35 hours. Profit on the sale of A is rupees 30 and B is rupees 20 per unit. Formulate the LPP to have maximum profit. Here we have to formulate the LPP to have maximum profit. Means we have to maximize the profit. Therefore here profit is the objective function. Now we formulate the problem. First step is identify the decision variable. Here in this example, let X be the number of gadgets A produced by the firm, Y be the number of gadgets B produced by the firm. Now here X and Y represent the number of gadgets. Therefore both are greater than or equals to 0. Therefore X is greater than or equals to 0, Y is greater than or equals to 0. Since the profit on the sale of gadget A is rupees 30 per unit and on sale of gadget B is rupees 20 per unit, the total profit is equals to 30x plus 20y. This is a linear function which is to be maximized. Hence, it is an objective function. The given information can be tabulated as follows. Now, from this table, we can say that in foundry, total man hours of labor requires for X unit of gadget A and Y units of gadget B is 10x plus 6y hours and the maximum time available is 60 hours. Therefore, 10x plus 6y is less than or equals to 60. This is the first constraint. Now in machine shop, total man hours of labor requires for X unit of gadget A and Y unit of gadget B is 5x plus 4y hours and maximum time available is 35 hours. Therefore, 5x plus 4y is less than or equals to 35. This is the second constraint. Therefore, LPP is as follows. Maximize Z is equals to 30x plus 20y subject to the constraint 10x plus 6y less than or equals to 60, 5x plus 4y less than or equals to 35, x is greater than or equals to 0, y is greater than or equals to 0. In board exam, this sum will ask for 3 marks. Problem 2. A doctor has prescribed 2 different kinds of food A and B to form a weekly diet for sick person. The minimum requirement of fats, carbohydrates and protein are 18, 28, 14 units respectively. 1 unit of food A has 4 units of fat, 14 units of carbohydrate and 8 units of protein. 1 unit of food B has 6 units of fats, 12 units of carbohydrates and 8 units of protein. The price of the food A is rupees 4.5 per unit and that of food B is rupees 3.5 per unit. Form the LPP so that the sick person's diet meets the requirement at a minimum cost. Here we have to formulate the LPP to minimize the cost. It means here objective function is cost. So to formulate this problem, we know that first step is identify the decision variable. Let X unit of food A and Y unit of food B be prescribed in the weekly diet of a sick person. Now here X and Y are the units of food. Therefore, they are greater than or equals to 0. Therefore, here X is greater than or equals to 0, Y is greater than or equals to 0. The cost of food A is rupees 4.5 per unit and food B is rupees 3.5 per unit. Therefore, total cost is equals to rupees 4.5x plus 3.5y. Now, this is the linear function which is to be minimized. Hence, it is the objective function. The given information can be tabulated as follows. 1 unit of food A contains 4 units of fats, 14 units of carbohydrates and 8 units of protein. 1 unit of B food contains 6 units of fats, 12 units of carbohydrates and 8 units of protein. And minimum requirements of fats is 18, carbohydrates is 28 and protein is 14. So from this table, We can say that weekly diet of a sick person has 4x plus 6y units of fats, 14 eggs plus 12y units of carbohydrates, and 8x plus 8y units of protein. And the minimum requirements of fats, carbohydrates and protein are 18, 28, 14 units respectively. Therefore, the constraints are 4x plus 6y is less than or equals to. Here, minimum requirements of fats, carbohydrates and proteins are given. Therefore, constraints are 4x plus 6y is greater than or equals to 18, 14x plus 12y is greater than or equals to 28, and 8x plus 8y is greater than or equals to 14.
वाढा वाढा माझ्या संगे वाढा वाढा माझ्या संगे वाढा 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 वाढा
ह्याप्रमाणेच मुलांच्या सोबत वाढत आहेत LICचे चिल्ड्रन्स प्लॅन्स, जे देतात आकर्षक रक्कम मुलांच्या वाढीच्या प्रत्येक टप्प्यावर.
वाढा वाढा माझ्या संगे.
Therefore, LPP is as follows. First, write down objective function. So, minimum z is equals to 4 point of x plus 3.5 y, subject to the constraint 4x plus 6y greater than or equals to 18, 14x plus 12y greater than or equals to 28, 8x plus 8y greater than or equals to 14, x is greater than or equals to 0, y is greater than or equals to 0. Now we'll see what is meant by convex set. Definition: a set of points in a plane is said to be a convex set if line segment joining any two points of the set entirely lies within the set. For example, first, if you observe these two diagrams, in this diagram, line segment joining any two points entirely lies in the set. Therefore, these two are the convex set and both diagrams are bounded. Therefore, we can say that convex sets may be bounded. Now observe these two diagrams. Here, line segments joining any two points of the set entirely lies within the set and both diagrams are unbounded. Therefore, we can say that convex sets may be unbounded. If you observe these two diagrams, here line segment AB does not lies entirely within the set. Therefore, these two are not convex set. Now we'll see solution of LPP. There are two methods to find out the solution of LPP. First is graphical method and second is simplex method. In this chapter, we will learn only graphical method. Now we'll see some definitions. Solution. Last year you have studied this. A set of values of variable which satisfies all the constraints of the LPP is called the solution of the LPP. Feasible solution. A solution of LPP which also satisfies non-negativity constraint is called a feasible solution. It means when solution lies in first quadrant, it is called feasible solution. Optimum feasible solution. Optimum feasible solution, a feasible solution which optimizes, that is either maximizes or minimizes the objective function of LPP is called optimum feasible solution. Feasible region, the common region determined by all the constraint and non-negativity restriction of the linear programming problem is called the feasible region. Now we'll solve LPP by using corner point method. So first of all, we'll see the steps. First step is convert all inequations of the constraint into equation. Second step is draw the lines in XY plane, and to draw these lines we have to find out 2 points on the line. Third point is locate common region indicated by the constraint, and this common region is called the feasible region because it lies in first quadrant. Find the vertices of the feasible region. Find the value of the objective function z at all vertices of the feasible region. If the objective function is of maximization type, then the coordinates of the vertex for which z is maximum gives the optimum solution. And if the objective function is of minimization type, then the coordinates of the vertex for which z is minimum gives the optimum solution. Note, if a LPP has optimum solution at more than one point, then entire line joining these 2 points will give optimum solutions. Hence, the problem will have infinite solutions. Problem: solve the following LPP by graphical method. It's a 4 marks question. First, maximize z is equals to 9x plus 13y subject to the constraint 2x plus 3y less than or equals to 18, 2x plus y less than or equals to 10, x is greater than or equals to 0, y is greater than or equals to 0. Solution: here objective function is maximize z is equals to 9x plus 13y and given constraints are 2x plus 3y less than or equals to 18 and 2x plus y less than or equals to 10. So to draw lines, we prepare the table as follows. Now we know that first step is convert the inequation into equation. So here first constraint is 2x plus 3y is less than or equals to 18. Therefore, first equation of the line is 2x plus 3y is equals to 18. Second constraint is 2x plus y less than or equals to 10. Therefore, second equation of line is 2x plus y is equals to 10. Now second step is find out the 2 points which is lies on the line. So to find out the points of first line means 2x plus 3y is equals to 18. First put y is equals to 0. Then you will get x is equals to 9. So first point is 9, 0. Now put x is equals to 0. You will get y is equals to 6. So second point is 0, 6. Now draw the line passing through these 2 points. Now here constraint type is less than or equals to 0. When constraint type is less than or equals to 0, then region is origin site. Second equation of line is 2x plus y is equals to 10. To draw this line, we have to find out 2 points. So first put y is equals to 0, you will get x is equals to 5. So first point is 5, 0. Now put x is equals to 0, you will get y is equals to 10. So second point is 0, 10. Now draw line through these 2 points. Here constraint type is less than or equals to, therefore region is origin site. XY plane. Now this is the line which is passing through the point 5, 0 and 0, 10. Equation of this line is 2x plus y is equals to 10 and region is origin site. Now second line is passing through the point 9, 0 and 0, 6. Equation of this line is 2x plus 3y is equals to 18 and region is origin site. Now x is greater than or equals to 0. This arrow represents y is greater than or equals to 0. Therefore here this shaded portion is the solution set. Now next step is we have to find out the corner point of the feasible region. So here corner points are A, B, C. Coordinates of A are 5, 0. Coordinates of C are 0, 6. Now coordinates of B, if you observe, point B is the intersecting point of lines 2x plus 3y is equals to 18 and 2x plus y is equals to 10. So to obtain the coordinates of the point B, solve these 2 equations simultaneously. You will get x is equals to 3 and y is equals to 4. Therefore, coordinates of the point B are 3 and 4. So from figure, the common shaded region OABCO is the feasible region with vertices O 0, 0, A 5, 0, B 3, 4 and C 0, 6. Now next step is find out the value of objective function z at vertices. So first vertex is A whose coordinate are 5, 0 and here objective function is z is equals to 9x plus 13y. So find out the value of z for x is equals to 5 and y is equals to 0. Put x is equals to 5 and y is equals to 0 in z, you will get z is equals to 45. Second vertex is B 3, 4. Now put x is equals to 3 and y is equals to 4 in z, you will get z is equals to 27 plus 52 is equals to 79. Third vertex is C 0, 6. Now put x is equals to 0 and y is equals to 6, you will get z is equals to 78. Fourth vertex is O 0 0. Put x is equals to 0 and y is equals to 0. You will get z is equals to 0. Now, if you observe this table, maximum value of the z is 79 occur at the point 3 4. Point B 3 4. Hence, optimum solution is x is equals to 3 and y is equals to 4. Second example, minimize z is equals to 7x plus y subject to 5x plus y greater than or equals to 5, x plus y is greater than or equals to 3, x is greater than or equals to 0, y is greater than or equals to 0. Here objective function is minimize z is equals to 7x plus y and constraints are 5x plus y greater than or equals to 5, x plus y is greater than or equals to 3. To draw lines, we prepare the table as follows. In table, first column is equation of line, means convert inequation to equation. So first constraint is 5x plus y greater than or equals to 5. So first equation is 5x plus y is equals to 5. Second constraint is x plus y is greater than or equals to 3. So second equation of the line is x plus y is equals to 3. Now find out the points. First put x is equals to 0, you will get first point. Then put y is equals to 0, you will get second point. So for first line, points are 1 0 and 0 5. For second line, x plus y is equals to 3, points are 3 0 and 0 3. Here constraint type is greater than or equals to. Therefore, region is non-origin site. Now, if you draw the lines, you will get such diagram. Equation of this line is x plus y is equals to 3. Now, equation of this line is 5x plus y is equals to 5. And this shaded region is the solution set. This solution set lies in first quadrant, therefore it is called feasible region. And vertex of these feasible regions are A 3 0, B and C 0 5. Now here B is the intersecting point of lines 5x plus y is equals to 5 and x plus y is equals to 3. So simplify these two equations simultaneously. You will get x is equals to 1 upon 2. Now put the value of x is equals to 1 upon 2 in equation 1. You will get y is equals to 5 upon 2. Therefore, coordinates of the point B are 1 upon 2, 5 upon 2. The common shaded region XA, B, C, Y is the feasible region with the vertices A 3 0, B 1 upon 2, 5 upon 2, C 0 5. Here region is unbounded. In last example, region is bounded. And in this example, feasible region is unbounded. Now find out the values of z at vertex. First vertex is A 3 0. So put x is equals to 3 and y is equals to 0 in z. You will get z is equals to 21. Second vertex is B, whose coordinates are 1 upon 2, 5 upon 2. So put x is equals to 1 upon 2 and y is equals to 5 upon 2 in z. You will get z is equals to 6. Third vertex is C 0 5. So put x is equals to 0 and y is equals to 5 in z. You will get z is equals to 5. Here we have to find out the minimum value of z. So if you observe here, minimum value is 5. So from the table, minimum value of z is 5 occur at the point C, whose coordinates are 0 5. Hence, optimum solution is x is equals to 0 and y is equals to 5. Let's solve one more example. Maximize z is equals to 11x plus 8y subject to x is less than or equals to 4, y is less than or equals to 6, x plus y is less than or equals to 6, x is greater than or equals to 0, y is greater than or equals to 0. Here objective function is maximize z is equals to 11x plus 8y. Constants are x is less than or equals to 4, y is less than or equals to 6, x plus y is less than or equals to 6. Now to draw the line, we prepare the table as follows. Here, first equation is x is equals to 4 because first constraint is x is less than or equals to 4. So first equation is x is equals to 4. Second constraint is y is less than or equals to 6. So second equation of line is y is equals to 6. Third constraint is x plus y is less than or equals to 6. Therefore, third equation of line is x plus y is equals to 6. Now we know that x is equals to 4. This line is passing through the point 4 0 and parallel to the y-axis. Here constraint type less than or equals to, therefore region is origin site. Y is equals to 6. This line passing through the point 0 6 and parallel to the y-axis. Constraint type is less than or equals to, therefore region is origin site. X plus y is equals to 6. Now to draw this line, find out 2 points. So first put y is equals to 0, you will get x is equals to 6. Therefore 6, 0 is the first point. Now put x is equals to 0, you will get y is equals to 6. Therefore second point is 0, 6. Constraint type is less than or equals to. Therefore region is origin site. XY plane. First we'll draw the line x is equals to 4. This line is passing through the point 4, 0. Then equation of this line is x is equals to 4. Now draw the line which is passing through the point 0, 6. And its equation is y is equals to 6. X is equals to 4 line. X is greater than or equals to 4. Therefore region is origin site. Y is also less than or equals to 6. Therefore region is origin site. X is greater than or equals to 0 and y is greater than or equals to 0. Now draw the line x plus y is equals to 6, which is passing through the point 6, 0 and 0, 6. Equation of this line is x plus y is equals to 6. Now this is the shaded portion represents the solution set of the constraint. Okay, now this solution set lies in first quadrant, therefore this is the feasible solution set. Now here if you observe, point B is the intersecting point of line x is equals to 4 and x plus y is equals to 6. So put x is equals to 4 in x plus y is equals to 6, you will get y is equals to 2. Therefore coordinates of the point B are 4, 2. The common shaded region OABCO is the feasible region with the vertices O 0, 0, A 4, 0, B 4, 2 and C 0, 6. Now next step is find out the values of Z at vertices. So first vertex is A40. For this value of Z is 44. Second vertex is B42, means put x is equals to 2 and y is equals to 2 in Z. You will get Z is equals to 70. Third vertex is C06. So put x is equals to 0 and y is equals to 6. You will get Z is equals to 48. And last vertex is origin. So put x is equals to 0 and y is equals to 0. You will get Z is equals to 0. From the table, maximum value of Z is equals to 70 occur at the point B 4, 2. Hence, optimum solution is x is equals to 4 and y is equals to 2. Student, I have told you this sum will ask for 4 marks. So this you will get first mark for the first table, then second mark for this feasible region, third mark for finding the values of Z at the vertices, and fourth mark for this last statement. So student, today we have learned meaning and mathematical formulation of LPP. Also we have studied to find out the solution of LPP by using corner point method. In this way, today we have finished this chapter. I hope you have understood it, and for practice you will solve example form exercise and miscellaneous exercise. Thank you.